The Ben Heck Show is brought to you by Element 14, the electronic design community and online store built for engineers and hobbyists alike. Join now and browse the store at element14.com.
Okay, so I got the Gatorade since you were talking about programming in a field and drinking it. I'm not sure why.
Oh, you might have had the kitten video volume up too loud when I was talking about this. It's Field Programmable Gate Array, an array of gates. FPGA, not Gatorade.
Oh, that reminds me, there's this video you have to see. It's a kitten and it's cuddling with a sloth.
Amazing builds, exclusive mods, cutting-edge ideas, electronics, engineering, and more. Every week on Element 14's The Ben Heck Show.
A few years ago, I saw a project at the New York Maker Faire that was using this weird widescreen LCD, like a 4:1 ratio. And I was obsessed with it because I'm like, oh, that's the same shape as a DMD in a pinball machine. And I asked the guy, where did you get that piece of LCD glass? And he said, hey, it was this weird car visor screen that I got off eBay. And I'm like, no way, I didn't know such a thing existed. So I got back home and I went on eBay, and sure enough, you can buy these weird car sun visor LCD screens. I'm not even sure if these would be technically legal in a car. Probably not, at least not on the driver's side. But hey, it means that a weird widescreen piece of glass exists, which is great. I'm like, oh cool, I can make a color display for a pinball machine that is the right shape. Because when people make color displays for pinball machines, which they do, they usually put a big LCD behind it, which sticks too high and too low. Basically is masked off by the window, but these would be perfect. The problem with these screens is that they're composite video only, which means even if you're just using a composite video signal like an old game console, it's still going to be stretched and squashed. It's basically worthless. So what I want to do is drive the LCD myself using my own custom controller. And for that, we're going to use an FPGA. The first step is to take apart the screen and find the signals. Taking the screen out of the plastic, it's the perfect size. If only it could run good video. Let's take a look at it. So this is our driver board. So your 12 volts come in from your car, along with your composite video. Again, bleh. We have an inverter over here, which creates the high voltage for the lamps. This is the part we care about. This is the signaling going to the LCD itself, and there's a separate driver board here. And that's what we want to actually take a look at. So I'm going to unplug this, making note of the polarity. So I've got two black wires on one end, so I made a black mark there. Carefully lift this up. So let's see, it's a Hitachi driver board. It's got a part number on it, that's good. It's made in Japan, that's surprising. And it looks like it kind of goes with this. So we don't need this, we just need this. So if we want to address the glass, this is what we do. This, we're still going to keep this for testing to power it up and to run the lights, but this is basically garbage. There's two black wires, which are obviously ground. Then these two wires are obviously positive voltage. I can tell by the fact they're going to a circuit. These two are ground. All right, so then aside from these two black wires, these are our power wires, and what's left are our signal wires. And we can kind of guess what it is just by looking at the number of them. See, we have white and then a color. Usually differential signaling wires, especially like in a video connection, are going to be white and then a color. So if you take apart an HDMI cable like we did with the Xbox One laptop, there was a white and brown pair, white and red pair, white and blue, and that's usually a dead giveaway that they're differential signaling. And if we look on the traces, we see that we have 4 pairs of 2 wires going to this. So this chip here is probably taking the differential signaling and turning it into kind of a parallel bus of signals. As you can see, a lot more connections come out of it than go in. So if we can get the right differential signaling into this chip, we can manually drive this LCD and give it the proper resolution, not crappy composite video. The plan is to use an oscilloscope to sniff the signals coming into this board from the original driver board to reverse engineer the signals. Before we do that, let's talk about what differential signals are. We're pretty sure this LCD uses differential signaling, but what is differential signaling? Well, it's basically two signals that are different. Here's an example. There'll be a differential pair of two wires like we found on the LCD, and if one wire has a higher voltage than the other, it's a 1, but if it's the other way around, it's a 0. So in this case, you can see the blue line goes low, goes high, goes low, goes high, and the red line, representing its differential pair, is the inverse of it, and that creates the zeros or ones. Now, why do systems use this? It's because you can get much higher speeds with it. If you don't have to go to a high voltage, it doesn't take you as long to get there. Okay, so how does this relate to our LCD driver controller? Well, I found some data sheets online, and this is how a lot of LCD controllers work, although we're going to have to reverse engineer the exact timing of that device. We have 4 differential pairs, and this drawing represents 1 pixel of data. So you basically have 4 streams of zeros and ones going into it at all times. One of the pairs is going to be the clock. You're going to have 4 high and 3 low, and so this will repeat, giving it the main pixel clock rate. And that'll be subdivided into 7 bits per clock to actually give you the bits of data. There's probably going to be an enable bit saying, is this pixel on or not? A V-sync bit saying, is this a vertical synchronization pulse? An H-sync bit for if it's at the end of the line. And then the RGB will be packed in the remaining bits. So you may have 6 bits of red, 6 bits of green, and then 6 bits of blue. So what we're gonna do is hook up the screen in its current form to the oscilloscope and sniff these 4 differential pairs and see if we can find some of these patterns, compare that to what's on the screen, and reverse engineer it. We have our standard probe here. I'm going to clip on this wire hook probe. See that? Makes it easier to hook up our connections. Let's hook up the 4 lines and then take a look at the data on the oscilloscope. I'm using the Tektronix MDO3104 oscilloscope. It has 4 channels, which is great for this because we have 4 differential signal channels. We could also use the logic analyzer, but I think this will be fine. Here are the 4 channels going to the LCD. At the top, we have a clock. See how it's really consistent. The next one down is pretty consistent, but you can see a little bit of it's changing. Once we lock into it with the trigger, we can get a better idea of this. This one, only 1 bit is set, and that's probably the LSB of blue. And down here, we don't see anything. Since most of the screen is blue, this bottom line is probably red. So I'm thinking that this is probably red, green, and blue. Now remember, there's a few bits of different colors in each one, but I think that's generally what we have here. So we have clock, control data, most of blue, some of blue, most of green, a little bit of green, mostly red. Let's look for a trigger point. Since it says no signal on the screen in red, there should be some red someplace. So what I'm gonna do is I'm gonna go into trigger, and I'm gonna set up a trigger on channel 4, which is gonna look for any high pulse. And again, this is fairly low voltage, but we still should be able to find something. Voltage level, let's just, oh, there we go. See, there is something there. Okay, so we're going to actually zoom out a bit. I'm gonna go to single. There we go, and we captured it. All right, I set a trigger point to look for red data, and this is what we have. There's a bunch of these, and what those are the pixels vertically going down that spell no signal. The fact that there's a mostly blue screen with some red text that says no signal makes it convenient for reverse engineering. See these right here? That's actually NOSIGNAL. So that's actually the top line of pixels for the word no signal. So if we look at it a little closer, let's zoom in here. We're just gonna zoom in on where it starts because the change in the pixels will help us reverse engineer it. See how we have the mostly blue line? So that's the upper 5 bits of blue and then like the lower bit. So this basically means a big blue pixel, but then it stops. But we still have a little bit of it left. Well, that's not actually blue. That's the data enable line we talked about on the whiteboard. So that one is always pulsing whenever there's a valid pixel. And down here, I'm actually gonna increase the time scale of that a little bit, turn off the menu. This line wasn't active before, but all of a sudden it is. See how it's completely on? Those are the 6 bits of red. So this is definitely where the word no starts to print. So the blue turns off and the red turns on. And see that right there? So we have 6 bits of red, and then the 7th bit would be green, but obviously there's no green there, so that one's low, and there's no green at all here. So it's definitely mostly red, mostly green, mostly blue and control bits. That blue spike right there is definitely the data enable bit. It goes high whenever there's an active pixel. All right, so now that we know that the frame is pretty similar to what we expected for a standard LCD, LVDS signal, we need to find the horizontal and vertical blank. Just like a composite screen, the digital signals will do something different once they've completed a line to tell the LCD that it's time to go to the next line. From a distance, we can see the blue pixels, the text pixels, and more blue pixels. And this is the front and back porch of the horizontal line. Front and back porch is basically invalid pixels before the visible pixels and after that are used as part of the syncing process. And inside of all these front and back porch pixels, we can actually see the horizontal sync bit being set right here. We have an enable bit, a V-sync bit, and a H-sync bit. So the enable bit is still low since we're in the front porch. Then we have 2 empty bits next to it. So the enable bit is right here, vertical sync bit and H bit. So all 3 of those are low. Right here, see how there's a shorter pulse? That's because the H sync bit has gone high. So that lets us know that horizontal and vertical sync is active high, not active low. And we can actually zoom out and count how many ticks of high horizontal sync we have. 20. So at the end of each line, there are 20 pulses of high on the horizontal sync bit. Then we have about 20 more null pixels, and then the visible data resumes. Okay, I've got the horizontal data written into my notes. It's probably not quite exact, but it should get us somewhere when we get to the FPGA. Now to find the vertical sync signals. I captured a larger amount of data this time, so we can see basically a whole frame. There's where the V-sync starts. There's the vertical sync's back porch. There's our text on the screen, all the lines of no signal, a bunch more blue, and then V-sync again. So we can definitely see where it's happening. It's very obvious, but we need to zoom in and take a look at what's actually going on. So I'm going to move past the no signal pixels and find that. You can actually see here from the horizontal sync, you can basically count how many lines there are. You can see the bumps in the data. All right, let's find this guy. Oh, there it is. It's pretty obvious, right? I'm going to count this before I zoom in. So we have 1 line of something and then 17 lines of something. So those are probably entire lines that have the enable bit as 0. So it's like 1 line, then 2 lines of vertical, then 17 lines of blank, and then repeat frame. Let's double check. Something's different here. You can kind of see patterns from a distance with the scope and then zoom in on them to double check. Oh, yeah, see this? So the enable bit is low, the horizontal sync bit is low, but the vertical sync bit is high. And it looks like it's high for 2 entire lines. Okay, we see this anomaly in the middle of it. This is where the horizontal sync is active at the same time as the vertical sync. See how the enable bit is still low, but then these 2 are both high? So that means our horizontal sync is constant. So even while the vertical sync is being activated, we're also activating the horizontal sync. So in our FPGA, we'll do the horizontal sync first, and then we'll add the vertical sync. So at the end of every frame, we have 1 line of disabled pixels, 2 lines with the vertical sync bit set, and then 17 more lines of disabled pixels, and then the frame repeats. All right, I think we're ready to move on to the FPGA portion. Let's try to drive this LCD with an FPGA, a field programmable gate array. That means you can program it anywhere, like in the field. And it's an array of gates. It basically becomes whatever logic circuit you want it to be. This is a Cyclone 3. It's on a dev board. We have our 4 differential pairs hooked up from the LCD into the dev board. We also have ground going to the LCD. And then we also have a heartbeat LED hooked up so we can make sure our program is working. We're using Quartus 2, which is a free download to actually program this. This isn't really going to be a comprehensive FPGA tutorial, but we'll show you the basics. Okay, we'll call this LCD driver. So the folder is called LCD driver and the project is called LCD driver. Yes, create the folder. We don't need to add any files yet. Okay. Select our family, Cyclone 3, and then this is the FPGA. Looks good. Don't need this. All right, finish. First thing we're going to do is add a Verilog file. So we're going to say yes for Verilog HDL. There's 2 main ways of programming these things, Verilog and VHDL. Verilog is a little, I don't say easier, but it's more like a structured language, at least from what I've seen. Let's just get this no file. And we want to save this top level file to have the same name as our project. So I'm calling it LCD_driver. Now an FPGA is basically logic. So it's not like a microcontroller. You can program it, but everything happens simultaneously. So it executes in a different way. The first thing we need to tell it is what our inputs and outputs are. So I've got an example here. All right, so we need to change the name of this. I got module bit clock, but again, this module has to have the same name as the file name. So these are the inputs and outputs. We are inputting the clock, which is the 50 megahertz crystal on this board. Then we have 2 switches. Then for outputs, we have the 4 pairs, pair 2, 1, 0, and clock. So it's going to be the green, the blue, the red, and the clock. And then we have an LED indicator, which is just our blinky light. Blinky light, very technical. Okay. Okay, module, LCD driver, and module. This is enough to do a synthesis, which will allow us to go into pin planner. Now that we did that, it knows kind of what's up. It knows the pins we've defined, so we can go into pin planner and see how they're down here. Everything is listed. Now we can assign them to actual physical pins on our FPGA. And I have a PDF for this dev board so I know which pins on the output header go where. Let me just start doing this here. So this is an output. So these are already, the output is already set up like for pair 0 and clock. So all you need is a location. So we're gonna go pin AA16. And I don't know if you can see it here in the capture, but it tells you that's, you know, pin AA16, and then it's the positive end of a differential pair. So if I go in here and say AA16, okay, so that's the positive end. Now for our I/O standard, we go from the default to bus LVDS. We don't have to use bus LVDS, but this portion of the chip, you can't use standard LVDS, but it'll still work. So when I click bus LVDS for that pin, it adds the negative pair. See? So we have the positive pair and automatically created the negative pair. So we can do that for the rest of the pins. I've assigned all of the pins, and as I click on them, you see them lighting up on the pin planner. I can also click on the pins in the pin planner, and we can see that the differential pairs are well paired. And the differential signals I have set to bus LVDS. So you only have to make one connection. It'll automatically assign the 2 pins for the LVDS, which is handy. Okay, looks like that's all ready to go. I also attached some switches because the dev board has switches on it, which we can use down the road. All right, so the main things we need are these 4 differential pairs. With those connections made, we can move to the actual clocking. We have a few conditional statements here. If H current, which is where the pixel is, if it's more than the front, or V current is more than the front, we turn off the enable bit that we found on the scope, else we leave it on. It's usually on. If we're at the end of the line where we found that horizontal sync pulse, we turn on the pulse for 20 pixels. Likewise, if we're near the end of the whole frame, we turn on the VSync pulse for 2. And I punched in the numbers, at least from the box. The box says 800 by 234 resolution. So that's what I typed in. We'll see if it's right. So we have 800 pixels, and then we have 327 blank pixels, and then the H-sync. So we'll see how close we got. I have a feeling it's not quite precise, but hopefully it's close enough to get something on the screen. The core of it is the bit selection. So the bit indicates which part of the RX data we're on. So it's going to do these bits first, then these, then down the line. And if you look at this one, the clock data bit, see how we have 11000011? That's our 4 up, 3 down clock signal to drive everything. Okay. If which bit equals 0, which means have we clocked out all of these and we're at the end, then we check to see if we're at the end of the line or if we're at the end of the frame. If which bit is not 0, we decrement the bit number to go to the next position. Let's give it a try. It did something. Well, it's not flickering. It looks like the horizontal resolution of the screen is actually greater than the box implies. I can't believe it. Also, the vertical resolution isn't correct either. See, here's the 234 pixels because we thought it was 234 pixels tall. It draws that, then there are those 20 blanking pixels we talked about, and then it starts over again. So obviously we need to find the correct vertical height and the correct horizontal width. So we're gonna have to dial in a few numbers and recompile. I told the Verilog to make the top, bottom, and 2 lines red, and the 2 leftmost and 2 rightmost lines green. And I've used that to dial in the actual resolution of the screen, which is 1024 by 310. So with those correct values plugged into the front and back ports of H-sync and V-sync, I have a complete frame. Now I can do cool things with it. And here we have all 3 colors on the screen making a cool pattern. Today's challenge was to reverse engineer an old random LCD and use it for something else. We accomplished that by using an FPGA to drive the signals that we reverse engineered using a Tektronix oscilloscope. It worked, so I am pretty happy with the result. Obviously, being able to use LCDs for multiple purposes is something that everybody has been asking about for years and years and decades in the hacking community. So it was great to actually take the time and figure out how to do it, especially with this cool widescreen LCD. Do you have any tips or suggestions as to how you would have done it? Let us know on the element14.com community. That's all the time we have for today. In our next episode, we're going to be revisiting the Pi MAME portable gaming system. We'll see you then.
So I got the Gatorade. I don't even know, wait, what was I gonna say? Now that I say that out loud, that sounds kind of dumb.
Gatorade is a Sarah McLachlan charity for alligators that need help. For 50 cents a day, you can help a struggling gator before it gets hit by a car in Florida by a redneck tourist. In the arms of the angel. The gator's like, we'll send you a photo of your gator along with its biography. Well, this gator was born in the swamp back in 1994. He lived a full life, but then he was hit by a car. 18 wheels, well, I guess 9, because, you know, they're on either side. Then he died. Like, really, what would you use that for? Okay, all these mistakes are really stupid, so don't use them. Let's skip this. Let's just show it being done right the first time.
The Ben Heck Show is brought to you by Element 14, the electronic design community and online store built for engineers and hobbyists alike. Join now and browse the store at element14.com.